Good morning everyone, and welcome to today's worked exam answer video. Today I've chosen a GCSE question, and I've chosen one that actually goes through quite a lot of different skills and different topic areas. So we're thinking about group 1 elements, and initially we're thinking about reactivity. So potassium being added to water in terms of observations and equation, and then why the reactivity of the elements changes as we go down group 1. So comparing potassium with sodium and lithium, and then the elements below potassium as well. Then we go on to thinking about structure and bonding. So we're thinking still about group 1 elements because we're thinking now about sodium, and we've got to draw a dot and cross diagram to show what happens when atoms of sodium and oxygen react to produce sodium oxide. Then on the back of the page it talks about reduction. Thinking about oxidation and reduction and the different meanings of those, and then thinking about structure and bonding again in terms of the properties of sodium oxide. So there is a lot going on in this question, and I will try and keep it as concise as I can, but we all know that I'm not very good at doing short videos. So if you are interested, please bear with. If you're interested in parts, obviously you can skip forward to the bits that feel most relevant for you. So let's crack on. So we're first of all asked to give 2 observations we would make when a small piece of potassium is added to water. Now there are some observations that will be present for any group 1 metal being added to water. The one that is specific for potassium, which we don't need to give, but because it's potassium we may as well, will be it will burn with a lilac flame. So that's going to be one of my observations. We would also see the potassium sort of moving on the surface of the water, and some of that is down to the low density of the first 3 group 1 metals. They all float on water, but the movement on the surface is a result of the gas that's being made, which is hydrogen, and kind of propelling it across the surface. So the potassium moves more vigorously across the surface than the sodium and the lithium. The other thing we can say is that we would expect to see some effervescence, although with potassium that's quite hard to see because of the burning with the lilac flame and because the reaction is quite quick. So yeah, those would be there, but it's how easy they are to observe. But we wouldn't be penalised if we did say effervescence for the reaction of potassium with water. Effervescence, fancy word for bubbles, can also say that as well. So yeah, I'm going to say effervescence, but moving on the surface of the water would also be absolutely fine. Okay, then we've got to complete the equation for the reaction of potassium and water. So we need to know the products that are being made, and it says we should balance the equation. So in terms of the general equation, any metal that is able to react with water will produce a metal hydroxide and hydrogen gas. So that's the first thing we've got to know, so that we can then go, okay, if we've got potassium reacting with water, we're going to make potassium hydroxide and hydrogen. Second thing we've got to know is that hydrogen is diatomic as an element, so it'll be H2. And then we also need to know how to put together the formula for the potassium hydroxide. So potassium as an ion has a charge of plus, and the hydroxide ion is OH minus. So in terms of putting those 2 ions together in a compound, which should have no overall charge, we're going to have KOH as the formula there. I don't feel like they're giving us enough room for this. And then when it comes to balancing, this one's quite tricky because we've got currently 3 hydrogen atoms on the right hand side, and we've only got 2 on the left, and it's hard to make, well, very hard to make an even number into an odd number. So what I would advise is that we start by making the number of hydrogens on this side bigger than 3. And the other good thing is we've got 2 hydrogens here and 1 here. So because the hydrogens are in both products, we can look to maybe double everything in this compound so that we get 2 hydrogens from here plus 2 from here to make 4, and then we can balance that on this side. So I'm going to put a 2 in front of the KOH, which will then give me 2 Ks, 2 Os, 2 H's plus the 2 H's there, so a total of 4 H's on the product side. Then I can balance the H's by putting the 2 in front of the H2O, which will also balance out my oxygens, 2 O's, 2 O's, and then I just need to sort out the K's. So I can also put a 2 in front of the potassium. Now, if you are comfortable, you can put a half or 0.5 in front of the H2 and leave all of the others with no balancing numbers. That would achieve the same effect. Fractions are okay if you've got still a whole number of atoms, if you will, when you finish. So 1.5 H2, that's fine, because that would give you 3 atoms. You couldn't put 1.5 or half even, or any half, in front of something like K, because that would give us half a K. Okay, but that's possibly the safer route to go with. Okay, then we've got to think about explaining why the reactivity of the elements changes going down group 1. Now, they haven't said how it changes, and that's one of the things that we're going to need to say for our 4 marks here. So I know it says explain why it changes, but the first thing we're going to have to do is state how exactly it changes to then be able to explain it. So the first thing that I'm going to write, just go back and put my bullet points there, is that the group 1 elements get more reactive as we descend group 1, and that is illustrated by the metals moving faster across the surface of the water, the reaction occurring faster. So the lithium will sit and fizz for a while on the surface, whereas the potassium is kind of put it in, sets on fire, burns with a lilac flame, moves on the surface very quickly, and then the reaction is done. So both of those are indicators that the group 1 elements get more reactive as we go down the group. What we need to think about now is why. Why does that happen? So even if you weren't sure, we can have a think about, in terms of the positions of these on the periodic table, what happens to the elements as we go down group 1. Well, first of all, they have higher atomic numbers, so more protons in the nucleus. Because we're thinking about atoms as well, that therefore means they've got more electrons. And we know that each electron shell can only hold a certain number of electrons. So if we're thinking about the electron configurations, for lithium, it would be 2 in the first, 2 electrons in the first shell, then 1 in the second shell. For sodium, which is underneath lithium, 2 in the first, 8 in the second, 1 in the third. And then with potassium, we would have 2 in the first, 8 in the second, 8 in the third, and 1 in the fourth. Now that sort of trend would continue, but you wouldn't at GCSE have to go any further than that. So even if we didn't know what was going on, one thing we can observe is that actually as we go down the group, the atoms get bigger. There's more electrons, there's more electron shells, the atoms are larger. That's definitely got to have some sort of effect. So we'll put that bit next. So this is because the atoms get larger as there's more electrons and more electron shells. And then we've got to think about what that means for reactivity. So electron configurations govern everything to do with how an element will react, whether that's the number of shells that they have or the number of electrons in the outer shell. That is what dictates chemistry. When we're thinking about these metals, they want to become ions, and to become ions, they need to lose the electron in their outer shell. So elements are happiest when they have a full shell of electrons. That's why the noble gases are so happy to just stay as noble gases and not really react with anything, because they have full shells of electrons. And every other element would like to achieve that. So these group 1 metals are going to lose this electron on the outer shell, and therefore it has to be easier for potassium to lose that electron if the potassium is most reactive. And it is easier for potassium to lose its electron because the distance of the outer electron from the protons in the nucleus is greater. The electron is further away, so the attraction of the protons in the nucleus to the electron is weaker, so it's easier for the electron to be lost. And that is how we tie in the size with what needs to happen to these atoms in order for them to react and become compounds. So this is because the atoms get larger as there's more electrons and more electron shells, comma, meaning it is easier for the atoms to lose an electron and become ions as the attraction between the protons in the nucleus and the outer shell electron is weaker. There we go. So trend is they get more reactive down the group. Why? Because the atoms get larger. How does that help us? The atoms want to lose an electron, so the larger atoms will find that easier to do because the protons are not holding the outer electron quite as tightly. Hopefully that makes sense, and don't ever be afraid to write out some electron configurations, because I think that can be really helpful, not just for thinking about reactivity, but also thinking about what we're about to have a look at, which is dot and cross diagrams. So don't ever be afraid to write out the electron configuration, and if you've got questions on how to do that, again, please just ask. So in the next part, we're looking at sodium, and we're told that sodium reacts with oxygen to produce the ionic compound sodium oxide. Now, that's very nice of them to tell us it's ionic. If they hadn't said ionic and just said to produce the compound, we would know it's ionic because sodium is a metal and oxygen is a non-metal. And whenever we have a metal and a non-metal reacting, the electrons will be transferred and we'll end up with ions and thus ionic bonding and a giant ionic structure. More on that in a second. So we have to draw a dot and cross diagram to show what happens when atoms of sodium and oxygen react to produce sodium oxide. So the first thing I'm going to do, as I've just said, that might be helpful is think about the electron configurations of sodium and oxygen. And sodium we've got from up there, so 2A1. Oxygen is 2, 6, so 2 in the first shell, 6 in the second shell. Now, again, going back to this whole idea of these elements having full outer shells of electrons, all their inner shells are already full, we would be looking to transfer the outer electron from the sodium across to the oxygen. And if we did that, this sodium would have 2, then 8 for its shells, so that would be happy. But the oxygen still wouldn't quite have enough. It would then only have 7 in its outer shell, and to fill that second shell it would need to have 8. So this is where we need to appreciate that we're going to need a second atom of sodium, also configuration 281, and then that outer electron can also be lost, will also go to the oxygen's outer shell, and then the oxygen will also be an ion, happy with its full outer shell. So that is what is going on, and if it helps to write out the electron configurations to see that, do it. Now, we could again then have a think about what the ions are going to be like in shorthand. So the oxygen has gained 2 electrons, so it's going to become 2, 8, and gaining 2 negative electrons will give it a charge of 2 minus. Both of these sodiums will then be 2, 8, and they've both lost an electron, so each of them will have a charge of plus, and then there's 2 of them. And just like we do when we're writing formulae, we can put the little 2 down the bottom here. But now I'm going to have to actually draw it as dots and crosses. So it doesn't specify about drawing the outer electrons only, or whether you draw the inner ones. Because there's only going to be 1 inner shell on each, I'll draw the inner shell, but if it specifies, please do as it requires. So I'll put my sodium in there. Also always label which ion is which somehow. So sodium is 2 and then 8 on the outer shell. And I know it had 1 on its outer shell initially, but don't draw an empty circle. Once that electron has gone, we only draw the shells that then have electrons on them. And then square brackets around those, and then our charge, which is plus, and then the fact we've got 2 of them. You can draw it twice, but that makes more sense. Takes less time. Now, it's called a dot and cross diagram. I've chosen to use crosses for sodium. Could I have done dots? Yes, I could. So long as one atom has dots and one has crosses, it doesn't matter. So now I'll draw my oxygen. Got 1, 2 in the first shell, and then it's going to now have 8 in its outer shell. So originally it had 6 of its own. So 1, 2, 3, 4, 5, 6, and then the 2 that it's gained from the sodium, we're going to keep those as crosses because that then shows where those electrons have come from. And that's why dots and cross diagrams are very useful. So then we can put square brackets around there, and then the charge at the top, 2 minus. We only need 1 oxygen. So that's a dot and cross diagram when we've got ionic bonding. And if it was covalent, it would look very different. And if it hadn't have said that this was an ionic compound, the temptation might have been to draw outer shells overlapping and electrons being shared. Please always check what type of elements we have and what type of bonding, therefore, they would engage in, and thus what type of diagram to draw. And again, if you're not sure, please just ask. Okay? And then whizzing on to the back for our final 2 questions. It says, why is oxygen described as being reduced in the reaction between sodium and oxygen? So there's different ways we can describe oxidation and reduction. So we've got oxidation being gain of oxygen or loss of hydrogen, reduction being loss of oxygen and gain of hydrogen, but the one that's going to be important here, we can remember using oil rig. And you may have heard of this, I'm sure a lot of you will have. If you haven't, I can explain. It's just a little, and I'm going to use the wrong word here. I was reading a post on this the other day about the differences between acronyms and mnemonics and all that kind of stuff. And I would have called it a mnemonic, but I could be wrong with that. But it stands for oxidation is loss of electrons, reduction is gain of electrons. So because we've drawn a dot and cross diagram and we've thought about where the electrons are going, sodium is losing them, so oxidation is loss, so the sodium's been oxidized, and because the oxygen has then gained those electrons, reduction is gain, the oxygen has been reduced. So essentially we're given the definition of what we mean by reduction in terms of electrons. Now, we could say very generically the oxygen has gained electrons. I would always specify how many electrons have been lost or gained. So if I was thinking about the sodium, I'd say each sodium atom has lost 1 electron. I wouldn't just say the sodium has lost electrons, plural, because that's not technically true. So here I'm going to say the oxygen atom gained 2 electrons, and that's all I'd need to say. Reduction is gain, so that's the proof. Okay. Finally, explain why sodium oxide has a high melting point. Again, we've got to explain. We've got 3 marks here. So we know it's got ionic bonding because it said that on the previous page. But I guess the first thing that we should be thinking about in any question like this is, what bonding is there? What structure does it have? What forces are we trying to break? That could be bonds that we're breaking or forces that we're overcoming. And how much energy it's going to take to do that. So those would be my prompts for your answers when we're thinking about structures and properties of different compounds. So the first thing I'm going to say is that sodium oxide exists as a giant ionic lattice and is held together by strong ionic bonds and then these ionic bonds take lots of energy, and it needs to be energy rather than force, lots of energy to break. Now, sometimes with ionic bonding, they want you to specify exactly what we mean by an ionic bond. I don't know why this is ionic bond specific, but we could say, we could add into here just to make sure we're covering ourselves, if you will. These ionic bonds, brackets, the strong electrostatic forces of attraction between the oppositely charged ions, close bracket, take lots of energy to break. And because this is worth 3 marks, I don't think that that's going to be necessary here, because we've talked about the giant ionic lattice, the fact that their ionic bonds are strong and that they're going to take a lot of energy to break. But because they did mention ionic bonding on the previous page, it might be that it is actually necessary to say what an ionic bond is. And I think that can cause a little bit of confusion in itself. That is a definition of an ionic bond, which I would recommend that you learn, A, so that you can regurgitate it, but B, so that it makes a little bit of sense as to what an ionic bond is. So when these atoms in our diagram either lost or gained electrons and formed these ions, the ionic bond is nothing inside the sodium on its own, and it's nothing inside the oxide ion on its own. It is then the sodium ion attracting the oxide ion. That is our ionic bond. And so we would have loads of sodium ions and loads of oxide ions in our giant structure, and we have to overcome the attractions between all of them in order to melt sodium oxide. So that is why the melting point is so high. So hopefully that's been useful. Any questions about any aspect of that, please do not hesitate to get in touch. And if anyone has any requests for similar questions or different questions that would be useful for them, again, please just let me know, either in the comments or on an email. Thanks so much, guys. Hope you have a lovely rest of your day.